Okay, folks, I am going to go through the problem that I assigned earlier, and I'm going to show you two different ways to go about solving this problem. And so to begin with, I am going to do it the way I would have done it, but I will say after talking to a student, I saw an alternative route that I thought was kind of cool and wanted to go over that. That will require uh, deriving an equation to see how it works. So let's give it a shot here. So I'm going to show you how I would have solved this to begin with. First of all, I would know the chart. I would know the structure of tyrosine. Make sure I got that squared away. So if I were to draw it, whoops, my drawing is pretty bad. So if I were to draw tyrosine, I would draw it like this. Okay. Okay, I drew it in its fully protonated form, and the pKa groups, I'll just write them right underneath just to keep it so that we keep them straight here. Okay, using the groups that I said to use up there. All right, so first of all, the first thing I'm going to do is get a sense of where my pH, which I wanted to know what is the net charge on this amino acid at pH 10.4. Okay. And at pH 10.4, I can kind of look through right away and begin a process of kind of just roughing out what I'm going to expect. So I'm going to expect that with a pKa of 9.4, 9.04, at a pH of 10.4, the pH is greater than the pKa, so that this will be mostly in its deprotonated state. So honestly, most of it will look more like this. Whoops. Let me try that again. Whoops, hit the wrong button. So it'll be H2. Most of it will be like that in its deprotonated form. How much of it, that's something we'll have to figure out. Now, if we look at the alpha carboxyl group and we think about how is it going to be drawn, okay, well, the pH at 10.4 is way above this, so most of it is going to be deprotonated again. So we'll just deprotonate it. Okay, so most will be deprotonated at that high of a pH. In this one, the R chain, the pKa of the R group, well, 10.4 is pretty close to 10.1. So we're going to say that it's, there's going to be a portion of it, a significant portion of it's going to be protonated, and a significant portion of it's going to be deprotonated. Now, it will be more deprotonated than protonated because the pH is higher than the pKa, but it's in the buffer region. It's plus or minus a pH unit. And so by definition, it's going to have a significant amount of groups present. So this will be mostly deprotonated if you go by the majority. The majority of this will be deprotonated, so there'll be still a significant amount that's protonated. So it will either be the protonated form, or as I have it written, O minus. So OH or O minus, and they're going to be a certain fraction is going to be the negative, and the certain fraction is going to be the protonated form. Whenever you're 3 pH units or so away, let's just play the game. Uh, uh, if you're so if we were to work, I say play the game, what I mean is let's do a little thought experiment. Okay. So we have pH is equal to pKa plus the log of A minus over HA. Okay. And so, and we said the buffer region is pretty much where you have essentially, you have, if I were to take pH minus pKa, make that equal to the log of A minus over HA, okay? And then I can take 10 to the minus pH minus pKa, all right? And then I can go A over HA, okay? Now, what this allows me to do is kind of, we can kind of do a little bit of some math here to um, to come up with some ratios here. So in the case when it's a 1 pH unit above the pKa, so when pH minus pKa is 1, in other words, then you have 10 equals A minus over HA. So you're going from one region where you're tenfold, the base is tenfold higher than HA, and when the pH is minus pKa is minus 1, then that ratio goes from A minus to HA. Okay. And so the buffer region kind of folds between these ratios when A minus is 10 times greater than HA, down to a range where it's 1/10 of that. Outside of that range, there won't be enough of the base or the acid present in order to truly be an effective buffer. Outside of that region, you can easily overwhelm the buffer with very little addition of acid and base. Okay, so that's when we say the buffer range holds between the pKa plus or minus 1. So if the pH is within the pKa plus or minus 1, that would give us that buffer range. And essentially, if we're talking about the presence of the conjugate base and conjugate acid pairs, you see that they range between these two ratios. That's what this is saying. Okay. So obviously, once you get outside of a pH unit away, then you're going to diminish the buffering capacity because there's going to be significantly less A minus and HA around relative to one another. And you lose the buffering capacity. And therefore, the fraction of COO minus, for instance, is going to be very different, be very, in this case, high. So let's just kind of play around with this one here, and let's just see what range we're dealing with here and here, okay? So if we have, so 10 to the 10.4 minus, what is it? What did we have? 2.24. Okay. That's going to be equal to 10 to the 8.16 power. And that's going to then be equal to, let me plug that in. to the 1.44 times 10 to the 8th. So that's equal to the ratio of A minus to HA. And if you see how huge that number is, in other words, we're saying the amount of HA that would be around at that point. Whoops. I am so sorry that I did all that for nothing. I'll just, so when we take 10 to the 10.4 minus 2 point, so these things, okay. So if I do that for our, I'm really sorry, I didn't realize that things weren't showing up on the screen as well. Anyway, hopefully it shows up in the video better. So if you figure out what the for the 2.24 and you want to know how much of the base is present versus the acid, and you go through these steps, okay, you're going to see that the ratio of A minus divided by HA is going to be vanishingly huge. I mean, it's going to be huge. So much so that the amount of HA that will be present will be diminished, hardly significant. So at this point, I would argue you could treat this as just a whole number one, because the amount of HA that's present is going to be insignificant. So you can ignore how much is there and just say all of it's A minus. So by just doing that alone, we can automatically, if we were to keep track of things, so the charge then on the alpha carbonyl group is going to be minus. So it's going to be -1. And let's look at this group here. Okay, let's do the same treatment. Let's see how big the ratio is. So if we go 10 to the, so 10 to the 10.4 minus 9.1, no, 9.04 minus 9.04. Okay, if we do that, all right, then, and we do all the math involved, that's equal to 10 to the 1.36. I'm having trouble writing. Too much coffee this morning already. Okay, 10 to the 1.36, and then if we take that, that becomes 22.9 is the ratio, which is A minus. Now, we're at a point where that ratio might actually be something we need to be thinking about. So, in other words, there may be enough charge here to consider. And even though most of it's going to be unprotonated, which in the case, if I were to write this, let me write this a little better. Since we're dealing with a nitrogen in this case, we can write it this way, where the acid is the protonated form carries the positive charge, and the unprotonated form has no charge. So this is how I would think about it for nitrogen. So I'd say there's going to be a super small amount of the protonated species that but is it enough to add any significant positive charge? Well, we'll include this one in our next set of calculations. So the one I don't even have to really think too hard about is the final one, we're looking at the tyrosines group here, right? So that one has both negative charge and protonated species, and of course that's because we're at 10.4 is well within a pH unit of 10.1, and so we know that I'm going to have to really consider that, because there's no doubt I don't have to do this mess here. We're within a pH unit, so I'm going to have to worry about the fact that there's a fraction of negative and positive, negative and neutral. Okay, so now I've kind of worked this out. Where am I going with this? I already know that I can say safely the alpha carboxyl group contributes a -1 to the overall charge. The alpha amino group is going to be fairly close to 0, but there may be a small amount of positive charge, and we will look at that. And then the R group, we don't know the charge yet. Okay, so what we have to do is ultimately we need to figure out, in the case, we'll start with the easiest one, which is the one that we need to be working on right here. We need to figure out the mole fraction of the base form, because it's the part that has the negative charge. So if we're looking here, we want to know what mole fraction of the deprotonated form is existing, because that mole fraction then will tell us what the charge will be. Okay, so just as a reminder, a mole fraction is abbreviated this way, X. It's like I think it's capital Chi, if I remember correctly. So we want to know for tyrosine, so this will be for tyrosine, we want to be able to calculate what fraction is negatively charged and what fraction, just what fraction is negatively charged. And to get that, we need to know the moles of A divided by the total number of moles. Moles of A divided by the total number of moles. And so that's where we want to get, because then whatever that fraction is, we multiply that by -1, and we'll get the partial charge on tyrosine. What fraction, mole-wise, is negatively charged of the whole? Okay? So let's make this easy by assuming that the moles of A minus plus the moles of HA equal 1. We'll just make it very easy for us, okay? We assume that the moles of HA plus the moles of A minus equal 1. All right? That's an important assumption we can make. And now we go and use our Henderson-Hasselbalch equation. So we know that pH is equal to pKa plus the log of A minus over HA. And our goal will be to go from here to figuring out the mole fraction of A minus. So that's what we're going after. We want to know the mole fraction of A minus so we can multiply that by -1. So we need to figure out, if we have a total of 1 mole, the sum of A minus and HA is 1 mole, we can get the ratio to give us the desired pH from the Henderson-Hasselbalch equation, and then use this relationship right here, moles of A minus plus moles of HA plus the ratio. we'll have two unknowns, we'll have two equations, and we'll be able to get how many of the 1 mole of the total species is A minus. That's what we're after. So let us do that. Okay, so I'm going to put in my numbers: 10.4, 10.1 plus the log of A minus over HA. And usually we use concentrations, but since this is all happening in the same volume, the same container, this also applies to moles. So what I'm saying is, since both the A minus concentration and the HA concentration are in, they're in molarity, and they're in the same container, so they're in the same volume essentially, the volume terms can be ignored, and whatever that ratio is in moles is also the ratio in molarity, it turns out. So we can just treat these as moles, is what I'm saying. It's a little shortcut, a little way of thinking. So then I can go ahead and begin the process. 0.3 is equal to log A minus over HA. And then, whoops, I accidentally erased everything. A minus over HA. Then take 10 to both sides. I get 10 to the third. 10, sorry, that's not what I meant to do. 10 to the 0.3 is equal to A minus over HA, which, let me do my calculator here, 1.995. So that's the ratio. So now I can set up in a substitution where I can substitute for A minus. I get 1.995 minus, HA. And then I can take this here and I can put in place of A minus, I can put 1.995 HA plus HA is equal to 1. And now I can solve for HA. I know that HA is 2.995. HA is equal to 1. Therefore, the number of moles present in this buffer, where I assumed there was only a total of 1 mole of substance, is 1 divided by 2.95. Sorry, 2.995. And what that gives me is 0.33, we'll say 4 moles. And then I can just subtract from 1 to get me the A minus, because I know that A minus plus HA equals 1, so 1 minus HA is going to equal then the A minus number of moles, which will be what is it, 666. Ooh, that's like the mark of the beast. So now I got these, and I can go back now and calculate the mole fraction. I know what A minus is, and since I know the total is just 1 mole, because that's my assuming, then I can say that I have 0.666 moles over 1 mole. Okay, so that cancels out moles there, times minus 1. And now I know that the contribution of charge from the tyrosine is going to be minus, so that's times minus 1. 0.666. Woo, that's kind of heinous. So if I go all the way back up here, I know this is going to be minus 0.666. All right. So, and now I have to figure it out, do the same thing, but this time for the amino group. For this guy right here, the amino group. Boy, I hope that you saw all my math, hopefully. Okay, so then, so I got, that's where I get my minus 166, I mean my minus 0.666. So if you go through everything, then you go through each step that I just did, you can see how I got first HA, then I got A minus by subtracting from this guy here. And I realized, I hope you can see this. It's hard for me to know how this is going to turn out in your view. Anyway, that being said, you get this final situation because we got the mole fraction of A minus by taking moles of A minus divided by total moles times the charge. All right, so we did that. And now we can do one more. We can go through the same series of steps that I just did here, but with, whoops, for the alpha amino group. Okay, and I can go through and I'll just set it up. And then so 10.4 minus 9.04 is equal to the log of A over HA plus, because remember I'm doing that so I remember which thing I need to do the mole fraction for. And if I do all of this, I will get so when you do this, you'll get 22.9 is equal to A over HA plus. And then, so I can do a different substitution since I really want to, I'll do the same kind of thing. A is equal to 22.9 HA. And then I can then say, okay, 22.9 HA plus HA is equal to 1. And so 1, so HA then is equal to 1 over 23.9. And if I do that, I get, whoops, hold on a minute. I hit a wrong button on my calculator. This is equal to 0.0418. So the number of moles of HA is pretty small, 0.018. And then I can do my mole fraction of HA, and that's equal to 0.0418 divided by 1. And I can just multiply that by plus 1. And I get 0.0418. And I'll just say it's a plus 0.0418. So it's a small amount. Does it make a difference? Probably not a whole lot, but so this will be, whoops, this will be plus 0.04, what did I say, 18? Yeah, 0.0418. And once I go through all those steps, I now add them together, and that sum represents the net charge. on that group at pH 10.4. So let me add them together. I get a minus 1.62. And if I didn't include that, let's say I just called this 0, I would get a minus 1.666. So, that I would say I you're probably now. What do we conclude from this? Well, if we're looking at this now, I feel like the part that's going to be helpful for you is let's just agree that if we were more than 3 pH units away from the pKa, we can treat whatever that charge is as a whole charge, whether it's 0, 1, or minus 1. So let's say if it's within 2 pH units, you would probably have to go through this calculation. Outside of that, you can make the same kind of conclusion we drew for this one, where we can just, it's essentially all the deprotonated form. So here's the bonus material. Is there another way to do this where you do a little derivation? Okay. Is there a way to come up with an expression that you can use from the get-go? Okay. And I'm going to say, yes, there is. And so we're going to start with pH is equal to pKa plus the log of A minus over HA. We will also assume that A minus plus HA is equal to 1. So we will make that assumption. And by being able to do that, we will be able to come up with expressions to avoid to have to go through all these steps, where we can kind of bang them out in one really nice equation, depending on if you're trying to solve for mole fraction of A minus or mole fraction of HA. So that's what we're going for. Okay, so the first things we do, very similar to what we've already done, except we won't put in values, we'll keep in the variables. The big challenging things here is we again, just to be clear, here's what we want. We want to know what A minus divided by 1 is, and we want to know what HA divided by 1 is. In other words, we want to know what A minus divided. So generically, we can kind of put it this way. Okay, so we're trying to figure out how can we solve for the mole fractions for both of these. This would be the mole fraction of A minus. This would be the mole fraction of HA. We've seen how we use the mole fractions, but it took a little bit to get to those mole fractions. So is there a way we can come up with a final sort of expression where we don't actually have to calculate what HA and A minus are? Is there a way to simplify? Yes, there is. So let's, there's a couple of ways we can go about this. I'm going to take kind of a longer way because I want you to see the parallels, okay? So, so here's what we're going to do. We're going to first, so we know that we're going to try to isolate either A minus or HA to begin with, and let's do A minus. So let's just do the algebra to isolate A minus so we can see what A minus is equal to when we get it all solved. Okay, so let's come up with a real simplified way of doing that. So here we go. So we take, so let's begin the process, pH minus pKa. So I'm now trying to simplify this, going to the log of A minus over HA, and I can get rid of the log by taking 10 to the pH minus pKa is equal to A minus divided by HA. Remember, where I'm going is I want to figure out a way to figure out what A minus is equal to without having to know what HA is. Sounds crazy, I know, but bear with me. Okay, so I know that HA is equal to 1 minus A minus. Okay, so I can substitute in for HA. So I'm going to 1 minus A minus. Yay. All I did was replace that, and that's equal to 10 to the pH minus the pKa. And all I'm trying to do is make it so that the A minuses are the A minus is on one side of the equal sign and everything else is left over. That's the challenge. So I'm going to multiply both sides by 1 over A. Okay. And that's equal to A minus. Now, the trick here is I want to get A minus on one side and everything else on the other side. And I got A minuses right now on both sides. So I'm going to distribute this 10 to the pH minus pKa. So what that leaves me with then is 10 to the pH minus pKa. All right, because I multiply it by 1 minus A minus times 10 to the pH minus pKa, and that's equal to A minus. Okay, so now I'm going to get 10 to the pH minus pKa is equal to A minus plus A minus plus A minus times 10 to the pH minus pKa. All right, and now I can distribute out the A minus. So now I have 1 plus 10 to the minus pKa minus pH. I'm sorry, 10 to the pH minus pKa. Get myself all screwed up here. Okay, and this will be 10 to the pH minus pKa. All right, and now I can get my A minus is equal to 10 to the pH minus pKa. divided by 1 plus 10 to the pH minus pKa. So now, oh darn it, I hit the it's on my stylus for my iPad. If I squeeze the pen, it turns into an eraser, and that's equal to A minus. And so if I want to know the mole fraction of A minus, all I have to do is take 10 to the pH minus pKa, okay, all over 1 plus 10 to the pH minus pKa, and I can know the mole fraction of that because A minus, I'll just remind you, A minus divided by 1 is the mole fraction. So if I'm just dividing this by 1, I can substitute in for A minus and I get this, and dividing by 1 just means it's 1. So I can put in the values and let's double check. Okay, we did this one up here and we got minus 0.666. So let's put in the values now. So 10, and we already did some of the math here, to the 0.3, because that's the difference between pH. 10 to the 0.3, right, because that's what we get for pH minus that, divided by 1 plus 10 to the 0.3, 0.3. And if we do that math, what do we get? If we do that math, what do we get? Well, we will get 1.995 divided by 2.995, and that's equal to the mark of the beast, 0.666 moles. I mean, mole fraction is 0.666, which is multiplied by minus 1 gives us minus 0.666, because that's, we calculated for that. So you can see, so in the end, you could actually just use this equation to figure out what the mole fraction of A minus is, and you'd get the charge. Now, how would you do this for HA like we had to do up here? We had to use HA to get 0.041 for the alpha amino group. So let's do the same thing, but this time instead of solving for the mole fraction of A minus, let's see what the shortcut method for the mole fraction of HA is. Okay, so we start off everything the same. You would only try to solve for the mole fraction of H plus, HA plus, if you knew, if you're trying to figure out the positive charge. You would use this method if you're trying to figure out what the negative charge was, because the unprotonated species would be negative. You would use this approach when the protonated species is positive and you're trying to figure out what mole fraction exists. So we make the same assumptions as before. A plus HA plus is equal to 1. So moles of each, and we'll do this all in moles again. So then we go through all the steps, and so I'm going to jump a few steps here now. So pH minus pKa is equal to A over HA plus, and so then we'll want to do a little replacement here. So we'll have 10 to the pH minus pKa. So that's pH minus pKa. And we're going to do a little replacement where we're going to say A is equal to 1 minus HA. So we have 1 minus HA here divided, HA plus, I mean, divided by HA. So I'm just substituting in for A. Okay. And then I'm going to continue to move down. And again, I'm going to take the same thing. I want to set HA on one side of the equal sign and everything else on the other side. And again, the idea here is we can then solve a problem like we did above, like we did here. We solved the problem without even needing to know how much A and HA are present. All we needed to do was input in the pH and pKa values, which are the experimental values. So if you know that, you can do that every time. And so working through all that, we will then do the math. So I'm going to have 10 times pH minus pKa times HA is equal to 1 minus H, so that's multiplied, 1 minus HA plus. Now I can subtract. So I got 1, and then I'm going to add HA plus to both sides. HA plus times, 10 pH minus pKa plus HA plus. So I got that now. Now I can go ahead and pull everything over, and I can say, aha, HA plus times 10 to the pH minus pKa plus 1, is I've distributed out HA plus, is equal to 1. So I can get HA plus is equal to 1 divided by 10 to the pH minus pKa plus 1. And again, now I got it so that if I know the pH and the pKa, I can figure out how many moles of HA plus are present, but I could also divide by 1, and that would give me the mole fraction. HA plus is then equal to HA plus divided by 1, because we assumed 1 total mole. And then we can go ahead then and say, okay, so 1 divided by 10 to the pH minus pKa plus 1, and all that divided by 1. I'm not going to bother with that because that just leaves us with 1. Now, in principle, I could come up with the answer, if I just go 1, 10 to the, and if we go back up here, I think we figured out the difference between pKa is 22 point, no, sorry. I jumped the gun here. So 10.4, 1.36. So I know that it's 10 to the 1.36 plus 1. Okay, 10 to the 1.36 plus 1. And if I look at that, then what do I get? I get 1 divided by 22.9 plus 1, 1 divided by 23.9, and 1 divided by 23.9 is, drum roll, 0.0418. And since that's charged, it's positive charge. So you could see I got the same answers 2 different ways. So let's clean this up a little bit so it's not so ugly. So if you're ever doing this, if you can assume 1 mole, which you usually can when you're not given a concentration or any set amount of moles, okay, then it's very easy. You can then go ahead, if you have 1 mole total. In other words, let me be clearer. If you can assume that A plus HA is equal to 1, then the mole fraction of A is equal to, and I'll try to draw this in my nicest handwriting penmanship here. So mole fraction of A is equal to 10 to the pH minus pKa divided by, and I got to look again just because I don't, oh yeah, 1 plus 10 to the pH minus pKa. All right, so that will always give you what A is, and if A is A minus, of course, then that will give you what the charge is. And then we can, if we want to know what the mole fraction of HA is in the same scenario, well, that's equal to 1 divided by 1 plus 10 to the pH minus pKa. That will give you that mole fraction. And so all of this to say you could solve all your answers by just doing that. By doing that for each group that has a certain charge, you pick out which one is the one you want. So to remind us, I'll go back now and I'll put a minus sign here. This is for when the base is negative, and this is for when the acid is positive. Hopefully, this long drawn out thing helps you. Amen. Let's hope.